For this video, the last video in section 12.3, we're going to be finishing up this problem. In the previous video, we saw the solution to this baseball problem. We found the maximum height reached by the baseball, and we determined that it will indeed clear the 10-foot high fence located 300 feet from home plate. The last part of this question is to find the range. In other words, the distance from home plate. How far is that ball going to travel? Okay, now recall that we have already determined the equation for the position for the vector valued function r of t equals 50 square root of 2t I plus 3 plus 50 square root of 2t minus 16t squared. We came up with this graph on our calculator by using parametric mode, and we were able to see that the ball is going to go up in the air and it's going to come back down. The ball did reach its maximum height when the the vertical component of the velocity vector valued function was equal to 0. And that was at about 2.2 seconds it reached its maximum height. Now to find the range, we want to find the location of this x-intercept. Where does the ball indeed hit the ground? When you're looking at where it hits the ground, the vertical component of position, the j part, will equal 0. So we want to determine how far this ball travels before it hits the ground, and we're going to set this j part of the position vector valued function equal to 0. So we have 3 plus 50 square root of 2t minus 16t squared. We want to know when that equals 0, because at that time the vector valued function for position will give you some x value, some distance to the right, and a distance vertical of 0. And you may recognize this as a quadratic equation. If we rearrange the terms a little bit, starting off with a negative 16t squared plus 50 square root of 2t plus 3 equals 0, you see that this is a quadratic equation with a equals negative 16, b equals 50 square root of 2, and c is equal to 3. Again, this is in the form of a quadratic equation, ax squared plus bx plus c equals 0. To solve an equation that is a quadratic equation, you can do this by factoring, by completing the square, or you can use the quadratic formula, where x is equal to the opposite of b plus or minus the square root of the quantity b squared minus 4ac, all of that divided by 2a. This is going to give us two solutions, one when we use the plus sign and one when we use the minus sign. We'll have to go back to the problem to determine which one of these is going to make sense. Now, since you're taking this as a Calculus 3 student, you have used the quadratic formula many, many, many times. So I will go and show you how I would do this on a graphing calculator that will just save us a little bit of time in our solution here. On the graphing calculator, such as a TI-83 or 84, you can store values into variables. And since we want to use a quadratic formula where a is going to equal negative 16, b is going to equal 50 square root of 2, and c is going to equal 3, I can plug those values into the variables. So I'm going to first start off with my a, which is negative 16. I type in negative 16 first, and then press the STO button, that's the storage button, and choose the letter alpha A and press enter. Now when the calculator views the letter A, the value is going to be assigned negative 16. For B, we have 50 square root of 2. I'm going to use the arrow to the right, and I'm going to store that into the letter B. And then I'm going to take 3 and store that into the letter C. So now the calculator will substitute those values when you plug that into an expression, and it will simplify it. So we want to enter the quadratic equation. We'll do it first with a plus sign, making sure you put parentheses around the whole numerator. I'm going to type in negative b using the alpha button plus the square root of b squared minus 4ac. The positioning of the parentheses is going to make a big deal here. So if you get a different answer, you want to go back and make sure that you're putting in the parentheses in all the right places. I'm going to put parentheses around the whole numerator and the whole denominator, plugging in actually the letters A, B, and C instead of those values. Now when you do this with a plus sign, you get one solution to the quadratic equation is t equals a negative 0.042. Let me skip that over. So one solution to this quadratic equation is t equals about a negative 0.04. So at a negative 0.04, it actually doesn't even make sense that the time of negative 0.04 would be useful in this problem since time is dealing with the amount of time after the ball has been hit. When t equals 0, that is the point where the ball is hit. We want, if we're looking at t equals a negative value, it simply won't make sense for this problem. So using the quadratic formula with a plus sign does not give us an answer that will be useful in this problem. So let's do the same thing. Instead of a plus sign, do it with a minus sign. And you can save yourself a little bit of time here by going back to the last entry, press second and enter. The last thing entered is going to be displayed, and I'm going to use the cursor to get to the plus sign and change it to a minus sign. Everything else is going to be the same. Press enter, and we see that the other time when the vertical component of position is equal to 0 is the time at approximately 4.46. I want to store that into a value, so when I go to the trace feature, I'll be able to enter the complete value instead of a rounded value. So I'm going to store that into the letter D. The letter D, that's the time where the vertical component of the position function is equal to 0 at approximately 4.46. So we can disregard the negative value for time. So doing this with a minus sign, we get t equals 4.46. To find the range, we want to plug that value back into the original position vector valued function. Now, I already have that stored in my calculator. In the graph mode, I went to the y equals in parametric mode and entered the original position vector valued function for the I and the j using the x equals and the y equals. Then I set up my window so that I could see the complete graph. I've already made those adjustments so you can see the entire path of the ball. Now we're going to trace and look at the time where t is equal to 4.46, but I stored that into D. So I'm going to press trace and press alpha D and enter. So you see at the time when t is approximately 4.46, x is equal to 315.47174, where y is equal to 0. So the location of the ball is 315.5 approximately up 0 at the time t equals 4.46. So at t equals 4.46, the range is approximately 315.5 feet. Okay, and you find that by plugging in r of 4.46. Will give us the information about the range.